this stuff.
Thank you.
So we started by introducing the idea of what current electricity actually is. It's this idea that charges move, and when charges move, you now have a current. Current's measured in amps. And so I is the symbol we use for current, measurement of Q, which is the amount of charge, not thermal energy this time, divided by time. Charge is equal to N, the number of charges, times the elementary charge, which is the smallest, usually we say protons and electrons each have a charge of 1, one's positive 1, one's negative 1. But that doesn't actually tell us anything. Relative to each other, that works, but as they are relative to actual current or charge carrying objects, the charge on an electron and the charge on a proton is 1.6 times 10 to the negative 19 coulombs. Obviously the proton's going to be positive, the electron's going to be negative. So if I want current, it's the number of charges times this elementary charge divided by the time they take to go past a particular point in the circuit. That gives you current. 1 amp of current is 1 coulomb per second, so that's going to give you a lot of electrons moving relatively quickly. Then we were talking about current flowing through a conductor unless there is a potential difference, which we also call the voltage. This is the thing that supplies the energy, whether it's a battery or whether it's a socket in the wall. These two different things, batteries provide DC current, electrical outlets provide AC current. As far as how they behave and what you guys are going to do with them, there is no fundamental difference. Once you get into applications of this stuff, you might start to address places where you have to take into account the fact that they're different, but largely we don't. And then we have to have a closed circuit. The current has to have somewhere to flow. The analogy that I gave you was that I compared it to like a river. And then in addition to current, so we talked about how a potential difference, we called that voltage. We talked about voltage down here. Voltage, V, is measured in volts, V. And it's the difference in potential energy per charge between 2 points. Things are only going to flow if they have potential energy and then need to use up that potential energy. And then resistance. Resistance is the other piece, how difficult it is for current to flow through an object. You need to have a certain amount of resistance, otherwise you could short circuit your circuit if there is no resistance. And that's how you blow up your battery or start a fire in an electrical outlet or that kind of thing. Voltage is measured in volts. Resistance is measured in ohms, this fun little symbol here, omega. And then the relationship between voltage, resistance, and current is given to us by Ohm's law. This was the original formulation of Ohm's law here in pink. The one in the green is the one that we use more often. Voltage is equal to the voltage required is equal to the current present times the resistance, or resistance is going to be equal to the voltage divided by the current. And when we start actually playing with this stuff, you'll see how that works out. Then we talk about electrical current. We said, okay, well, there's conventional current, and then there's electron flow, because the electrons are the things that are actually doing the moving. Protons do not move, because if protons move, that means the nucleus itself would be moving. And that doesn't happen. Otherwise, the whole object would just kind of be morphing as the current flew through it, and that doesn't make sense. So electrons are what actually flow. They flow from negative to positive. The conventional current, because we didn't know electrons existed, we didn't know that they were negative, conventional current goes the other way. It goes from positive to negative, and rather than fixing anything, physicists and electrical engineers just said, okay, we understand that we're wrong. We know that it's totally backwards. It doesn't actually change any of our calculations, so we're just going to leave it the way it is, and y'all can figure it out. So unless otherwise stated, we will always use conventional current, the assumption being that if protons flowed, this is the direction they would flow in, even though we know that's wrong, they don't. That's just what we do. So if I'm not mistaken, that was Wednesday, or whatever day that was that we last did this. And then Thursday, you guys were supposed to write me a test, and I was gone because my daughter was sick. Friday, you guys were all, you guys had Pro-D day. Monday was a holiday. Tuesday, you wrote me a test. Here we are, almost a week later, having accomplished nothing. Woo. So let's keep going. So, and Luis, yes, I have been recording this whole time. Because I was waiting for that hand to go up. Are you recording? And you didn't, so now I'm just letting you know. You're often concerned about this, so here we go. No. You cannot grab a crush. A loony. You got a loony, I'll sell you a cream soda. A buck? Sorry, what? A buck, yeah. Power, here we go. Yes, if you got a loony, I'll sell you a pop at the back of the class. I got lots of Coke and I got 4 cream soda crushes back there. So we've already talked about power. Power was equal to what? Sorry? We defined it as work over time. Work over time in words, not just the equation, is this idea here. It's the change in energy. I'll write it like this. Yeah, the change in energy, because work is equal to a change in energy, and this is the formulation we want to use. Should zoom in here a little bit. Power is the change in energy per time. Sometimes the language that you see here is the rate of change of energy. And as Gerkirch already said, we called it P equals W over T once upon a time. P was power. We measured it in watts. But there's got to be some sort of formulation here that we can translate this idea of work over time into electrical power. We had, I'll just give it to you and I'll show you how it relates. For electrical power, the formula we're going to use is power is equal to the current you have times the voltage. Now, current is measured in what units? Current is measured in amps. No, you're right. Let's just do this. Current was measured in amps, and now an amp, I'm just going down here real tiny. An amp is what? You said Coulomb, Connor, but it's not just Coulomb, it's Coulombs
times something. I think it's E or something.
Let's just go back here and take a look here. Coulomb per second. That's supposed to be an A. That's an A. Little arrow. Current's measured in amps, which is actually a Coulomb per second. I'll zoom in so it's really easy to see what's going on there. See, that's an A and then a Coulomb per second. Times by voltage. Voltage was a measurement of what? Did we have units for voltage? Ooh. Let's go back here and take a look at it. We called the units for voltage volts. We said it was big V. But I also said it was the difference in potential, or we know, how did I say it? Yeah. The difference in potential energy per charge between 2 points. So if we're looking at potential energy is also measured in what units? Sorry? Joules, yes, joules. Per charge, and charge is measured in coulombs. So a volt is actually equal to a joule per coulomb. Would have been useful if I wrote that down last week. So if we've got current measured in amps, which is also coulomb per second, and voltage, which is volts, which is also joules per coulomb, and I'm multiplying these two things together, what is a coulomb per second times a joule per coulomb going to give me? It's going to give you joules per second. My coulomb is going to cancel. And now what is a joule per second? No. It's energy per second, which is power, which is measured in. See, it all connects.
Always does.
You betcha. I being current, and V being voltage. Let's write it up here a little bit cleaner. A current is amps,
Can you zoom out, please?
which is equal to a coulomb per second. Yes, I would love nothing more than to do that for you, so you can actually see what's happening here. Which was a coulomb per second, and voltage, which is volts, which is also written as a joule per coulomb. So there we go. That is the relationship between power, current, and voltage. Now because we've got a relationship now between power, current, and voltage, and we have a relationship between voltage, current, and resistance, we can create two more relationships relating power, voltage, and resistance, or power, current, and resistance, by combining this equation here with this equation here. Okay? So if I take V equals IR, and we're going to start here for both of these. I got P equals I times V, and I've got P equal I times V. If I take this expression here, and I substitute it over here for V, what am I going to get? P is going to equal I times IR, which is going to give me P equals
I squared
yeah,
R.
yeah. P equals I squared R. So what that tells you is the power being used by a object in a circuit is going to be equal to the current flowing through that object squared times the resistance present in that object. That'll be how much power this thing is using. Conversely, if I isolate this equation for this guy here and then substitute it in here, if I first isolate, I'm going to get what? I equals V over R. And now I'll shove that right in there. I'm going to get P equals V over R times V, which is going to give me P equals what? Yeah, V squared over R. So depending on the information that's given to us, now we've got three expressions for electric power being used by an object in a circuit. Yes, Manuel?
Should we be putting this on a cheat sheet?
We will put all of them on the cheat sheet at the end in one big kind of, here we go.
Call it a cheat sheet. I think we should call it like
Your formula sheet?
yeah, historical honorable.
That's fair.
The education assistant page.
The educational aid. Okay, so 2 examples. Zoom in where here? Yeah, toss it on the desk and go get yourself a cream soda. De nada. Okay, we good? You put money up here. Is that a toonie? So I need to make change, or are you buying 2? Sure. It's $1 a pop.
What do you have?
Coke and cream soda.
That's it.
That's all I got.
You can do better.
Oh, you can grab the Coke as well.
No, in lieu of. You can't take 2.
No, can I like switch it?
Yeah?
I thought, yes.
I mean, I'm sorry that none of them are cold, but Ref needs coming too.
Oh.
Love it. Okay, Luis, we good? Okay, there we go. So 2 examples. An electric fan has a resistance of 12 ohms and requires 0.75 amps of current to function properly. What voltage is required to operate the fan? Well, that's a great question here. What do we know?
There's 12 ohms of resistance.
So R is equal to 12 ohms, you betcha.
have a 0.75
Take change.
amp current.
So the current I is 0.75 amps, and I want to know what voltage is required to operate the fan. So I'm looking for V. So what relationship then are we going to use here? What am I looking for, Jasmine?
Volume.
What is
No, I'm not. No, I'm not.
V equals IR? Love it.
I'm not.
Okay, so the current flowing through the lamp is 3/4 of an amp, and the resistance of the the fan, is 12 ohms. So what is the voltage required to operate that fan? You could use a calculator, or you could just tell me what 3/4 of 12 is. It's 9. 9 volts. So what kind of device, or what could we use to power this fan?
A battery.
What kind of battery?
Car battery.
One of those,
Hey.
right? So when we've got a particular setup, when we know the kind of current we've got, we know the resistance, this is what determines the size of the battery that you need to use to power these objects. Practical applications. Now, to answer the question Jasmine was trying to answer earlier, how much power is going to be used by the fan? Jasmine, what equation am I going to use here? We could.
No, just use P equals IV.
We could use P equals IV. We could use P equals V squared over R. We've got all of the information. We know V, I, and R, so it doesn't actually matter which one we use. Jasmine, which one do you want to use? P equals IV. Okay, cool. So then the current is 0.75. The voltage is 9. What's 3/4 of 9? Sorry? It's 0.75 times 9. Thank you. 6.75 what? Units on power are? Watts. Done. Next one. I've got an electric heater emitting 1 times 10 to the 2 or 100 watts of power when connected to a 120 volt power line. What is the resistance in the heater? So you plug in the heater. We know it's a 100 watt heater. This is like the kettle we had before. This is a pretty weak heater. 100 watt heater is not much. My kettle was 1500 watts. When it's connected to a 120 volt power line. 120 volts is coming from where? If you had to go out into the world and find a 120 volt source, where would you go? To the wall. Yes. No, not to the window. The window doesn't have an outlet. The walls are where the outlets are. And it's a heater, so the rest of the song actually would kind of work. But we're not going to sing the rest of that song, Manuel, because it's vile. 120 volts is what is the potential difference provided by an outlet in a wall in North America. Europe, 240. Brazil, is it 240 in Brazil, or is it 120 in Brazil? You can plug something here from North America into the wall in Brazil and it doesn't blow up?
The only difference, like
The shape?
Yeah, the shape.
Yeah.
Different.
So what's the resistance then going to be in the heater? We know that P equals 100 watts. We know that the voltage is 120. Connor, how'd you do it? You're wrong, though.
What? What do you mean?
You are incorrect, sir.
Wait, what?
I want to know what the resistance is.
No, P equals IV. You have a voltage, you have power. powers, so all you need to do is solve for I.
I want R though.
I'm not giving you R. Use the I and then
Sorry?
all of the sums.
P equals V squared over R. Yes, I'm hearing loud from the side and whispers from the front. P equals V squared over R. And now solving this thing for R, I'm going to get R equals what? V squared divided by P. Very good. Thank you, Jasmine. So my voltage is 120. So I'm squaring 120. I'm going to divide that by 100. 12 squared is 144. So 120 squared should be 144,000. No, 14,400 divided by 100 is going to give me 144 ohms. So as far as electrical applications are concerned, lots of these things are things that you, more than anything we've done before, are like real world constraints we put on things. If you want your object to be powered by the wall, it has to be provided with 120 volts. If you want it to be provided, if you want power to be in the form of a battery, you've got multiples of, what are these things, 1.5? Yeah, 1.5 volts.
Why do you have so many batteries?
Because I teach electricity in physics. I have lots. You know what happens if you take this? Do you guys know what a 9-volt battery actually is?
No.
It's this.
I'm not looking at it.
6 of these.
Boring.
Really?
I was
Scamming us?
expecting
Yes, all they do to make a 9-volt battery is they take 6 AAA batteries and smack them together.
boring.
That's all this is.
Wow.
Yeah,
I was expecting like something.
something fancy. I was too when I ripped open one of these with a set of pliers, and I was expecting something cool. I was not expecting 6 AAA batteries. But that's all it is. And so everything comes to you in multiples of pre-existing manufactured pieces. AA, AAA batteries are 1.5 volts. A 9-volt battery is a 9-volt battery. Car batteries have a particular voltage associated with them too. The wall is 120 unless you're in Europe, and then it's 240. Resistors, whatever resistance you need, you can go out and find an object with that resistance. This, more than anything we've taught you before, has real-life physical restraints when you're building some of these things. Now, what you want to do is, before you actually start building electric circuits, is we want to draw them schematically. Because if you don't draw them first, then you can do what my buddy and I almost did in our second semester first year university lab and almost killed ourselves. We put a circuit together. We looked at it. We hadn't turned the switch on. We're like, yeah, this is going to work. We turned the switch on. We were standing a little distance, and the thing started to smoke. And my professor came over to us, and he's standing there. He's like, don't touch anything that you've done. He reached over to the wall, unplugged the power supply, and said, if you had completed the circuit by touching that object with your finger, you would have died. Because we short-circuited a pretty vital piece of equipment, and it had more than enough current flowing through it to seriously injure, if not kill us. So we draw them first, because electricity, more than anything, has real-world pain associated with it too. So to draw them, we are going to use something called a schematic diagram. This is a graphical representation of a circuit. That shows the components. How's it going back there? Simmer? Just printing? Excellent. That shows the components and connections using standardized symbols. So you should be able to take a schematic drawing. Once you understand what the symbols are, you could hand your schematic drawing to an electrical engineer from anywhere, and they should understand what you've got here. Again, just like math, or in chemistry, where we want to have standardized language that everyone can operate in, electrical engineering has this as well. So this symbol in a schematic diagram is probably going to represent what? A conductor, specifically a wire. And the function of a wire or a conductor is to do what? What is the purpose? Yes, I'm just going to use slightly different language, but yes. It allows the current, it's current flow. That's all we care about at this point, current flow. I've already given you the next diagram. I've drawn it once, we're going to draw it again. Looks like this. That thing there is, you think it's a battery, but it's not a battery. It's actually the language we use is, we call it a cell. The long side is positive, the short side is negative. It's also called a source. And typically this symbol is DC, direct current source. You put a bunch of cells together, now you have a battery. But a single cell is technically a cell. Battery is multiple cells together. This is a battery. This is a cell. Using the language that we're standardizing here. Nope. Cell solo, cells together equal battery. And the function here is a source of voltage. No. Someone's going to make that mistake, and it's going to be your fault, Manuel. Next symbol. That's a resistor. Sometimes we use that symbol just to demonstrate any load. And the function of a resistor is to do what? Yes. Well, to hinder the flow. And use voltage. The voltage has to be used up by something. If you don't use up the voltage, then all of that ends up back into the battery, and that's how you short circuit a battery, cause it to explode. It's a good time. Something looks like this. Or like this. You betcha. These are switches. This one's closed. This one's open. And the names are a little misleading here. Which one actually allows you to do something? The closed switch actually allows you to do something. An open switch doesn't do anything. So the purpose of a switch is to break or complete this, I'll say the circuit. Then you got one of these. Anyone take a guess at what that is? That is it's kind of.
High voltage.
No. Further away. Sorry? A volt. Meter. Yes. Okay. This measures voltage change or voltage difference.
That could be like considered like, for example, a lamp and a circuit could be gold meter. Like, I don't know.
I've run out of space here. 1 sec. Between 2 points. Okay, so that's a voltmeter. What's one of these? An ammeter. Measures current at one point. There's a whole bunch more of these things. We're going to draw some of them down here. As many as I have space for. There's this one. You want to take a guess at what that is? That's a lamp, yep. We've also got, ooh, there's this one. That is ground.
Really?
Yeah. We've got one of these bad boys.
Oh, not a battery? No, that's not a word.
What is it, Manuel?
I don't know.
That is a capacitor.
But there's two types of them.
There's
There's a polarized and the light for this person.
no, we're not even going to touch capacitors in this course. There's one of these. Looks like a resistor, not a resistor.
Grass.
A coil is, what does a coil do?
It enhances magnetic field.
What's it called? Starts with an I. It's there, Manuel. What is it? It's an inductor, Manuel. Yeah. If you're going into other things, then you've got ridiculous ones, things that look like this. If you're going into electronics, I gotta make sure I do this right.
That's all. That's what we call that. Do you actually know this? Oh, fuck. It starts with a TR.
It does starts with a TR.
It's transistor.
It's a transistor. Nice. There's one of these. As a diode. Think of a diode as a little light, a couple different colors.
That's a light in there.
But it's an example for of a diode that you people can connect to. Just the light emitting diodes, yes, are slightly different. There are more, but I don't think I'm going to give you any more. That's not true. I'll give you one more. See if Manuel knows what this one is.
I recognize it.
That's the last one I'm going to give you. There are more of these. There are whole books of these diagrams. Also starts with a TR, AN. No, that's something else. This is a transformer.
Oh.
Not the car that turns into a robot. It changes, or it can step up voltage, step down voltage. It can go from
That's how I was thinking.
like 10,000 volts down to 120 volts. This is so you need these to step down. So like we have these big high performance long transmission power lines. Like if you will go to Clearbrook Park, you see these massive. You can hear them humming from the ground. They have like 10,000 volts in difference between those wires in the ground.
So what about 3 kilos?
But several times over. And actually, it's not voltage that kills you. It's current that kills you.
Yes. Yes.
You can have like thousands of volts, and it's just going to hurt like a son of a bitch. But it's not actually going to kill you. That's how electric fences work. They have massive voltages, but really, really, really tiny currents. A 4 amp current is enough to kill you. So that's not a. That's it.
Okay, so hang on. Like.
If we're gonna get really technical, I can kill you with a paperclip and this 9-volt battery in my drawer.
Kidding, right?
No, I'm not.
The Wait, wait.
Absolutely, I could.
Hold up. So, hang on. With the voltage, what is, like, how does it transfer the voltage to make it, like, feel like a shock?
So what voltage is, again, remember what the language you have for voltage. Voltage is the potential difference between 2 points.
Right.
So you've got an area of high and an area of low,
And then
and it wants to bridge that gap. If you give it a bridge, now you become a source of current flow between a place of high potential and low potential.
And that's why they give it really low current, because otherwise you get current.
Well, the current is low because the resistance of human skin is really high. The amount of current is a function of the resistance of, remember, you've got this relationship here. You've got V equals I times R. So if I have a large voltage and a large resistance, the current's going to be small.
Right.
The voltage is what hurts you. Current is what kills you. Resistance is what your skin provides in order to prevent death from occurring.
How do you do the paperclip thing?
Exactly.
So the thing, that is highly specific. You need to get through the skin. That's what the paperclip's for. The inside of your body, phenomenal conductors. All those electrolytes, your blood, great conductors. Your skin, phenomenal insulator, which is why people survive getting hit by lightning all the time. Because it burns you greatly, it hurts, but it doesn't kill you. All you got to do is, one of these, and your heart's not actually that far in there either. So one of these and 2 paper clips, all you got to do is create enough current, to disrupt the heart muscle, because the heart muscle is just electrical impulses,
You may as well just stab him.
and you're dead. Oh, no. You can't. He's not going to stab him there with a paper clip's not going to kill him. You need the 2 paper clips and the 9-volt battery.
Whoa.
But that is beside the point. Yeah.
So you mean you would just have to break the skin? That's it.
No, you got to get a little ways. You have to be able to hit something with that current that's going to cause damage.
What about like a wound?
Yeah, like a cut.
Well, if I could, in one finger and one in another finger, and we like shove it in there, and then we run it through your chest, yes, it'll hurt. That'll probably kill you.
The real life.
Again, you need enough voltage, and you need a path. The path has to go through something vital. So if the path doesn't go through the heart,
What about your nervous system?
take my psychology course. That's a different story. Okay, here we go. So there are 2 ways you can attach a device to a circuit. You can either attach it in series or in parallel. Does anyone know the difference between series and parallel circuits?
Yes.
What is the difference, Manuel, between a series and a parallel circuit?
Can I give an example?
Sure.
Christmas lights. Like
Some are, some aren't. Which ones suck?
the old ones
Which are connected in?
in series.
Because when you have one bulb die, what happens?
Anything past that point will.
No, not just past. Everything will die.
Okay.
This is how old school, Manuel's right. This is how old school Christmas tree lights were set up. And they were in series. So if you have one bulb blow, the entire chain is useless because a series circuit only has one path. Only one path for current to flow. It's cheap, it's easy, but it's stupid. Because even if you find one that's burnt out, and it still doesn't work, now you got to find another one. This was my job when I was in leadership in high school. We had old school Christmas lights right before our Christmas banquet. Me and 2 buddies checked literally thousands of feet of Christmas lights. That was our job for like a week. That's all we did.
That's probably pretty fun.
We made it fun. So for an example, if I want to draw a battery of 2 cells connected to 2 resistors in series, I would draw it like this. Here's my 1 cell, there's my 2nd cell, connected in series with 2 resistors means I can only have one path for this whole beast to flow. So I'm just going to do this. There's my resistor, there's my other resistor, and we're done. This is a series circuit with 2 cells and 2 resistors. This is the positive side of those cells. This is the negative side of those cells. So conventional current, I, is going to flow that way. parallel is how modern day Christmas lights are wired. They allow multiple paths. For the current to flow.
Does that mean that this has like more wires?
You betcha. Yeah. So there's a bunch of different ways you can wire this thing into parallel. But it's slightly more complicated because if everything's in parallel, and you're relying on every light bulb being its own separate path, that means if a light bulb burns out, the whole rest of the thing stays the same. But you have the potential then for one of those paths having nothing on it. And so then you have to have resistors there that are able to compensate for that because you don't want to short out the whole system. If I wanted to draw a parallel circuit with two cells connected to two resistors, that would look like this. There's my two cells. Now, if I want my resistors connected in parallel, I'm going to have one branch with one resistor, and I'm going to have another branch with another resistor. So that at this point, my current is going to split. Some is going to go down this way. Some is going to go down this way. Yeah.
What happens when the battery like explodes?
Why does it explode? Because all of that, like the flow of electrons, heats up to the point where, because like these, they all have chemicals in them. These chemical cells. You heat up that cell until it reaches its ignition point. Now you have fire.
And in your case,
Yes.
with like the circuit and
The smoking circuit. Yeah.
So it was. You said you if you touched it or whatever, it would have.
We would have completed a circuit and it would have killed us. Yeah.
Okay, so that's what it was.
Yeah.
It wasn't the.
There was a lot of current running through a very small area. Yeah, and it would have been bad.
Got it. Okay. So it could have also heated up and exploded.
Oh, that's why it was smoking.
Got it.
Yeah. But that one wasn't a battery. That was plugged into a power supply. Like a physics table, big star power supply plugged into the wall. That thing would have continually fed power. There was no burning out. It was burning out the components in our circuit, not there was no battery there. We were providing a lot of voltage to a very delicate circuit. Not something you guys are going to do in high school.
If this circuit would be like
Flip the page.
was bigger, like that circuit, you need a corrector, it would be that too. Like if the circuit was bigger, like.
It all depends on what the current is. Current's the determining factor on whether or not you live or die. Doesn't matter what. Yeah, doesn't really matter what's going on in the rest of the circuit. So last piece here. It's taken us a while to get through, but that's okay. So for some of you, this is brand new because you didn't do this in grade 9, and that's totally okay. Well, it's not ideal, but we make do. So we take our time going through it. Measuring voltage and current. We can measure the voltage in a circuit using a voltmeter, which we already have a diagram for. And we measure the current in a circuit using an ammeter. I already drew those out for you. One is a V in a circle, one is an A in a circle. And the description that I gave for each one of those is determines how they need to get connected to a circuit. Voltmeter, I said, it tests the voltage difference between 2 points. So if you're connecting it to 2 points on a circuit, a voltmeter must be connected how? To be connected in 2 points means you'd connect it here and you'd connect it here. You're connecting it around other objects. So a voltmeter, by connecting it to a circuit, it's allowing another path for electrons to flow. So when you connect a voltmeter, you have to connect a voltmeter in parallel. Otherwise, it's not going to measure anything. because you have to connect it twice. It measures the voltage drop across a device. So for example, let's say I have a simple circuit. I have a couple AA batteries. Thank you. What device have I just created? Or a flashlight? Yeah. It's two 9 or two triple or two AA batteries and a light bulb. It's a flashlight. If I wanted to figure out what the voltage drop is across that light bulb, I would connect my voltmeter around the bulb like this. Because voltage is only ever, remember the definition for voltage, it's the potential energy difference. So for there to be a difference, you have to be testing it in multiple spots. If there is if there's nothing using the voltage in a particular area, it's not going to register anything. So like if I connected the voltmeter here and here, there's nothing using voltage in that wire, it would register as effectively 0. I want to figure out what my voltage drop is across the light bulb, because it's the light bulb that's going to use up some of that potential energy. Is that kind of making sense? Okay.
Are we going to
How about
do a lab on that?
Kind of. A voltmeter has very large resistance. We only want to test, this is a fun fact, want to test a few charges to see how much energy they have. If the voltmeter didn't have a large resistance, it would just allow the current to flow around the light bulb. The light bulb would turn off because no current would flow through it if this path is easier to flow down. So a voltmeter has massive resistance, so very few electrons actually want to flow through the voltmeter. The rest of them keep flowing through the light. You're not going to notice a dimming light if you connect a voltmeter to it because you don't want all that current to leave. So you test a few of the charges, see how much energy they have here versus here. An ammeter must be connected in series. This is because an ammeter measures the current through a circuit. You don't measure the current at multiple points, you measure the current at one point. So if I had my same circuit, and I wanted to measure the current there, I would have to toss my ammeter into the circuit in series. I'd connect it like that. Which I guess I should have also done in pink to match the voltmeter. And an ammeter has very low resistance. If I could spell resistance, that would be good. Because we don't want the charges to lose energy. As we test their current. Or I'll say as we count them, because that's really what we're doing. Voltmeter, huge resistance. Ammeter, almost none. In a perfect world, ammeter would have 0. And we've mentioned it before, so we're going to mention it again. The two different kinds of current. DC stands for direct current. Means it flows in one direction, such as current from a battery or a cell. And alternatively, you have AC current, which is called alternating current. And it alternates the flow of direction, and in the case of home electric circuits, it alternates at 60 hertz, so 60 times per second it changes direction. AC is more advanced than what we're going to be dealing with, so we're just going to ignore it. Because for the vast majority of the circuits you use, like even my laptop plugged into the wall, the reason that these things here exist, oh, it's plugged into there. Where's a better example? Sorry? Oh, yeah, there's another one before there. Thanks, you. Naya?
They even plugged into anything? No. It's not, you're just leaving it plugged into the wall.
This
It's a little waste of energy.
It's not plugged into anything. Is there anything flowing? So the whole purpose of this thing here is to convert the alternating current coming out of the wall into direct current so that my computer can not get fried by the alternating current coming out of the wall. Sorry? No. Manuel's trying to convince Connor to do something that's going to be harmful to him.
No. Oh, I thought you were going to get me paper clip.
I thought so too.
Like, I'm just saying your orange cord is plugged into the wall, but it's not connected.
Yeah, so if it's not connected to anything, is that a complete circuit? So is it using any power? No. You plug whatever you want in, as long as it doesn't go anywhere. There's no power being used. It's not a complete circuit. So that's that. I have an analogy here for series and parallel circuits, but I'm going to hold off on that because I want to see. Dare I?
No.
I'm going to hold off on this. Okay, so here's what I want you to do. Here's this worksheet here. I want you to play with the equations that we've got. Worksheet 6.1. I want you to do this. All of it. There's some graphing you're going to do there in question 10. I know you love graphing. Oh, it's analyzing graphs? That's part B. Analyze the graph you've just created. Tomorrow you guys are going to want computers. Bring your computers tomorrow. We're going to do a digital lab.
Do you know the order of your one?
Tomorrow is Thursday, so it's DCBA. You guys are the double block.
Okay, so it's
Second block. So yeah, we're gonna do a digital lab tomorrow. Make sure you guys have your computers here.
Is there a final exam after the 18th or before the 18th?
I have no idea. Probably the after. Whenever the last week of school is, it'll be there.
How much time we have to screw it up?
I guess the Wednesday of the last week of school is your guys', I think.
There's 4 more days?
I have no idea.
Wait, that's it?
Get to work on this. Shouldn't take you too long. See you later, Harshan.